We're continuing on here, chapter 13. And last time we got into gases. And we talked about some important units of gases. Probably the big three units are atmospheres, millimeters of mercury, and torr. Are probably the three common units that you come across most of the time. And again, the relationship between these different units is 1 atmosphere is equal to 760 millimeters of mercury and 760 torr, as a millimeter of mercury is equal to a torr. So it's like a 1-to-1 conversion between the two. So 760 is your magical number there to convert between them. If you have atmospheres and want either millimeters of mercury or torr, you're going to multiply by 760. And vice versa, if you have millimeters of mercury or torr and you want atmospheres, you're going to divide by 760. We talked about some gas laws here to start with. We talked about Boyle's law. And Boyle looked at the relationship of pressure and volume. And he held temperature constant and found that P1 V1 equals P2 V2. And once again here, we got constant temperature occurring. In terms of the units here, really doesn't matter as long as they're the same units on both sides. So pressure could really be any unit, again, if they are the same on both sides. And same thing with volume. Volume could be, again, any volume unit, once again, as long as they are the same on both sides. The sort of relationship that came out of Boyle's law was this relationship, sort of an opposite relationship. So as the pressure increases, we typically will see a decrease in the volume. And again, as we talked about, basically with a smaller volume, gas molecules don't have as far to travel to cause collisions. And again, the more collisions, the more pressure associated with it, and vice versa. Pressure goes down. That usually relates to the volume going up. And really, for the opposite sort of reason, as the volume increases, we're going to have less collisions occurring, and we are going to see sort of a decrease in the pressure. We then talked about two sort of gas laws, Charles' law and Guy-Lussac's law there at the end. And Charles' law is V1 T1 equals V2 over T2. Charles' law is at constant pressure, while Guy-Lussac's law is P1 divided by T1 is equal to P2 divided by T2. And this is at constant volume. And sort of the relationships that we see here in each of these cases, thank you, is in the case of Guy-Lussac's law here, as we increase the temperature, our gas molecules are going to fly around a lot faster, and that's going to cause a lot more collisions. In this particular case, because the volume is constant, the volume ain't going anywhere to help out. And because of that, we will definitely see that increase in those collisions, and we will see the pressure start to increase. And vice versa, if we lower the temperature, gas molecules going to be traveling around a little bit slower, going to cause less collisions in that volume. And the result of that is we will see the pressure start to decrease as well. Now, alternative to that is sort of Charles' law. And in this particular case, when we do kind of the same thing and increase the temperature, something different happens in this situation, and that is because we want to maintain constant pressure. So here our volume is not fixed, it can move. So what ends up happening in this case is, because our gas molecules are flying around faster, the volume actually adjusts and the volume will increase. And by increasing the volume, what that allows is to occur, even though they're moving faster, the gas molecules. And that, again, is basically how it maintains sort of constant pressure, is by adjusting the volume to sort of fit the temperature. And vice versa here, if we lower the temperature, once again, our gas molecules are going to be moving around a lot slower. And because of that, we would expect, for example, on the right there, that the pressure would start to drop. But again, because we want to keep constant pressure here, it's actually the volume that decreases. And by doing so, again, it allows these kind of slower moving gas molecules not to have to travel as far to cause those same number of collisions. And that, again, is what kind of keeps the pressure constant. So in Charles Law's situation, it's really that volume that's adjustable, that maintains that constant pressure. Because we don't have that in the Guy-Lussac's law, um, we are going to definitely see an increase in pressure with the temperature because, again, the volume's kind of fixed and rigid, will not go up and down, is basically fixed in place. One of the other things to sort of come out of this was really the bottom here on these gas laws is really every gas law. And as we saw at the end there, we did a graph of volume versus temperature for any gases you like, and you extend sort of that line to the temperature, it will always hit the same spot, which is that minus 273. Yes, help and recognize that as absolute zero. And what that essentially means is pretty much in all gas laws, the temperature needs to be in Kelvin. So you got to take your Celsius plus your 273.15 to convert it into Kelvin. And that is pretty much just like a always situation. Probably one of the first things you should do when you do the sort of gas law problems, if you have temperature involved, is definitely convert it into Kelvin. And again, as I mentioned last time, even in a situation where you may be given everything in terms of temperature in Celsius, and once again, maybe they may even ask you to solve for the temperature in Celsius, you do need to get it into Kelvin when it goes into the gas law and then do the conversion afterwards. Any questions on any of those things we talked about last time? All right, then I think we left off here at this example. So why don't we do this here? So take a few moments here. We got an experiment that has 452 milliliters of a gas used in a light bulb. It goes from 22 degrees to 187 degrees. What is the final volume? So take a few moments, see what you come up with. Okay, so let's take a look. And once again, as I mentioned maybe the other day as well, one of the good things to sort of maybe do in a gas law problem is just to pull out the information, maybe label it. So obviously here we have a volume that's 452 milliliters. We have a temperature that's 22 degrees Celsius. We have another temperature that's 187 degrees Celsius. And we're looking for a volume here. So again, just by simply labeling them, you could pretty much choose maybe the right gas law. Obviously, no pressures involved, so that eliminates those. So really here, Charles' law is the only gas law that sort of makes sense. Once again, in terms of the ones and the twos, it really doesn't matter as long as you kind of keep the numbers that go together. So I'm just going to call these guys the ones, call these guys the twos. And once again, I do know right off the bat, temperature's got to be in Kelvin. So we do need to add our 273.15 here, as they like the 0.15 here. So 22 plus 273.15. Gonna go 295.15 Kelvin, and our 187 plus 273.15 gonna be 460.15 Kelvin. So if we take our Charles law equation here, and in this particular case, we are solving for V2. Once again, when you do move something across the arrow, it's going to end up in the opposite location. So that guy will end up on top. Will give us V1, T2. T1 is equal to V2. Popping in our numbers here for our V1, 452 milliliters. Our T2, 460.15. And our T1 here, 295.15 Kelvin. Kelvins are going to cancel, going to leave me milliliters, which is good since we are looking for a volume here. And that's going to leave me 452 times 460.15 divided by 295.15. Going to leave me, we'll go 705 milliliters. And once again, if we think about sort of the relationship of Charles' law, in this case, what we see is our temperature went up. So we would expect our volume to increase. And again, it started at 452, ended at 705. So again, it So all right, the next law we're going to kind of talk about is Avogadro's law. And of course, our friend Avogadro, he had a number, but why not have a gas law as well? And if you remember Avogadro's number, it did involve our favorite thing, which is moles. And in sort of gas law, moles is abbreviated as an N. And it's not really surprising that his gas law also involves moles. And his gas law, and I'll write up here so you can kind of see a little better, maybe V1 over N1 is equal to V2 over N2. This is actually at two types of conditions. This is at constant pressure and temperature. So this is at constant pressure and temperature. Once again, here N is moles and V is volume. So much like other gas laws here, the volume again does not matter all that much as long as they are the same units. Obviously, N needs to be in moles for everything to sort of work out correctly. Um, The volume of a gas is proportional to the number of moles of a gas. So as the moles of gas increases, so does the volume of the gas as well. Now, you could use Avogadro's law just like any other gas law, which means if you got a couple of volumes in a mole, you can figure out moles, or vice versa. Got a couple of moles in a volume, you can figure out the other volume in terms of relationship. Now, another thing that sort of happens in terms of Avogadro's sort of relationship is, again, as you can see here, with one volume, we have 1 mole. 2 moles, you get 2 volumes of a gas. 3 moles, you get 3 volumes of a gas. So one of the sort of consequences of this sort of Avogadro's relationship that occurs when you have constant temperature and pressure is you could actually use it in stoichiometry. And it's sometimes, as we'll talk about a little later on this chapter, when we do sort of gas stoichiometry, a lot of times that involves using some type of gas law in the process. And if you happen to be under these conditions of constant temperature and pressure, you sometimes can sort of avoid the whole use of a gas law by using sort of Avogadro's relationship. And because Avogadro's relationship involves moles and volumes, if we were going to do sort of a traditional sort of stoichiometry relationship from this equation, we would come here and obviously from our coefficients, we would say, there's 1 mole of nitrogen for 3 moles of hydrogen, 1 mole of nitrogen for 2 moles of NH3, and so forth. Obviously, we could do 3 moles of hydrogen gives us 2 moles of NH3. So we can have our sort of mole-to-mole relationship like we would normally do in sort of a stoichiometry problem. But under these conditions, if we're dealing with a gas under constant temperature and pressure, we could actually do not necessarily a kind of mole-to-mole relationship, but we could kind of do a volume-to-volume relationship. And what that would look like, for example, is we could go to this equation and say for every 1 liter of N2, we would put in there 3 liters of H2. And again, the 1 and the 3 comes from the coefficients, just like we would do a mole-to-mole relationship as well. We could also say for every 1 liter of N2 we pop in there, we'll get 2 liters of NH3 out. And again, for every 3 liters of H2 we put in there, we'll get 2 liters of NH3. So for example, if you were doing this problem, and you had a question that asked you at constant temperature and pressure, if you started with 5 liters of N2, how many liters of NH3 would you produce? You could basically set up a stoichiometry problem using that kind of volume to volume relationship. And you could start with your 5 liters of N2, go to your equation, find sort of your volume to volume relationship. And once again, 1 liter of N2 will give us 2 liters of NH3. Liters of NH2 will cancel and will tell us that we will produce like 10 liters of NH3 in this case. And this can save you some time sometimes. Again, if you are under these sort of conditions of constant temperature and pressure in a normal stoichiometry problem involving gases, somewhere along the way, you'll be using some gas laws to kind of figure pretty much the same answer you'll get here out. And again, it could kind of save you a little work there sometimes. But once again, you can only use this sort of under law conditions, which are pretty much these right here. It has to be a gas situation, and you have to be at sort of constant temperature and pressure. Any questions on that there? Okay, so that's sort of a byproduct of Avogadro's law. And once again, like I said earlier, you also can just plug and chug into Avogadro's law, like any of the laws, and solve for whatever's missing, a volume, a mole, or whatever it may be. Now, putting together all those gas laws that we talked about, Boyle's, Charles, Avogadro's law, we get the granted them all there, the ideal gas law, and the ideal gas law is PV equals nRT. An ideal gas is a gas whose pressure and volume temperature can be accounted for through the ideal gas law. And really kind of, we think about ideal gases, although we don't get much involved in this class in terms of what sometimes referred to as real gases or non-ideal gases. But an ideal gas, basically, there's kind of two things that make something sort of an ideal gas. One thing is that an ideal gas, the volume of the gas itself is relatively small compared to the volume of the container it's in. And since the gas molecules are flying around, oftentimes when we are in an ideal gas situation, which is in most cases, we sort of think about more the volume of the container the gas is in rather than the volume of the gas itself. So if you read sort of gas law problems, you oftentimes will be told, not really the volume of the gas, but the volume of the container the gas is in. And it's sort of the same volume as the gas will fill it sort of uniformly. The other main thing that makes something sort of an ideal gas is the idea that under these ideal conditions, you could have multiple gas molecules in the same container, and there will be really no interaction between or even repulsion type forces between gas molecules. And in a sense, in an ideal situation, which in most cases we deal with, you can assume almost like the gas is in there by themselves. So they're sort of unaffected by other gas molecules that are flying around in the same container with them under sort of ideal conditions. And that's not the case, as you'll talk about probably in 1A. If you take 1A, you'll talk about real gases or non-ideal gases. And real gases and non-ideal gases happen at really high pressures, really low temperatures. And in those sort of situations, what occurs is you can't disregard the volume of the gas itself, nor can you disregard sort of the interactions between gas molecules, because frankly, under those conditions, the gas molecules are hanging around each other for a lot longer period of time. And also the volume of the container they're in is very small size. And you got to take the gas molecules sort of container into our volume into account as well. So for the most part, we deal only with ideal gases here. And for the most part, most of your gas dealings in chemistry, we do assume ideal conditions because you really have to get into some pretty high pressures for it to sort of deviate a lot from the situation normal conditions that we deal with. Most of the time, you deal with even if it's not kind of you're in perfect condition. So when we look at PV equals nRT, it is different than all the other sort of gas laws we've seen to this point. And one of the big differences is it's a one and done situation. There's no like two pressures, two volumes, two temperatures, or anything like that. So it's sort of like one set of conditions. The other really important thing about this equation here is it is the most restrictive in terms of units. So when you use this equation, everybody has to be in the proper units for things to cancel out correctly. So the units for pressure has to be an atmosphere when you go use the ideal gas law. The units of volume has to be in units of liters. Moles should hopefully be in moles, or something is probably definitely wrong. And temperature, probably no surprise here, does need to be in Kelvin. And the reason that all these guys has to be in sort of the correct unit is because of R. And R is the gas constant, and it is 0.08206 liters times atmosphere divided by Kelvin times mole. I personally use this number because that's what they beat in my head. But a lot of books nowadays will round a little bit to 0.0821. So either one of those are good. But you do need to know, yeah, the gas constant. And as you can see, the units associated with the gas constant there are liters times atmosphere divided by Kelvin times mole. And that is why everybody else in there has to be in those units. So a good way to remember that is, since you have to know the gas law constant and the units associated with it, it will basically tell you whatever unit to be for it to properly count. Any questions on that there? Now, a couple other sort of situations that we come across with gases, and we'll start down here, which is STP. And sometimes we have situations which are referred to as the STP condition. And STP stands for standard temperature and pressure. And actually, when they tell you it's under STP conditions, they are actually giving you both a temperature and a pressure value. So when it says STP conditions, they assume you know the temperature is 273.15 Kelvin and the pressure is 1 atmosphere, or obviously 760 torr, if needed. So sometimes that confuses people when they see STP in a problem. They're like, I don't have temperature or pressure given to me, but those are the values you should use. How do you use the ideal gas law? With STP conditions, it would be the 273.15, and the pressure would be the 1 atmosphere that should go in there. Now, there is a nice relationship that occurs under the STP condition, and that is if you are at STP conditions, 1 mole of any gas will equal 22.41 liters. So, relationship, if you happen to be at STP conditions, can save you some time. You don't have to use the ideal gas law that for times, and will not have to put things into the ideal gas law. Now, you should be cautioned that you should not use that conversion. It is only available to you if you're at the condition. If you're not at 273.15 and you're not at 1 atmosphere, you should not use that conversion factor. But if you be at STP conditions, then if you don't want to worry about using that incorrectly in a situation where you should not use it, once again, you can always use the ideal gas law. Doesn't matter if it's STP conditions, non-STP conditions, you can always use the ideal gas law. Just put the numbers in, everything will come out the same. So, that conversion only at STP, ideal gas law to use really under any conditions. And that is one of the things, by the way, when we were talking about a second ago about sort of ideal gases versus real gases. The ideal gas law is more like a universal sort of gas law. It works under lots of conditions. Start getting into gases and non-ideal gases. There's what's the van der Waals equation, which is a scary looking version of the ideal gas law. And there's a lot of constants. That's why a lot of times we assume ideal use sort of ideal gas law in this universal formula. By the way, this is where we do get our R value for. If we take the ideal gas law and we solve for R, it will equal PV over NT. And if you put in the values at STP, that would be 1 atmosphere for the pressure, 22.4 for the liters, 1 mole, and 273. That is, again, where we basically generate our gas constant from. By the way, not that we'll come across it too much, I don't think, in this class, but there are different versions of the gas constant. This is the one that you should always use for the ideal gas law. There is a gas constant that has energy units involved with joules and stuff like that. Don't use that one here. Anything like that. You want to use the 0.082 version. All right, so take a few moments here and let's try one here. Calculate the pressure in atmospheres exerted by 1.82 moles of SF6 gas in a vessel with a volume of 5. Okay, so let's take a look. Again, we pull out the information. We're looking for a pressure. We obviously have moles given to us, 1.82. We also have a volume of 5.43 liters and a temperature of 69.5 degrees Celsius. So again, looking at all the gas laws we talked about, obviously we only have one piece of information for each sort of variable. So that eliminates Boyle's, Charles, Guy-Lussac's, and obviously here Avogadro's. You could almost kind of see the ideal gas law by just kind of labeling everything here. And again, a reminder that probably never given to you in a problem, but again, a value that you always have is R. So again, it's usually never ever given to you in a problem. They just assume that you know you have that valuable available to you. So we obviously always have R available to us, which again, you do need to know 0.08206 liters, atmosphere, Kelvin, and mole. So really, we're good to go. We just want to make sure that we do have everybody in the proper units. So volumes here in liters, so that's good to go. Moles are in moles, so that's good to go. But very commonly as well here, our temperature is not good, so we do need to convert it there to Kelvin, and that's going to give us a 342.65 Kelvin. Now, if we take our PV equals nRT, we're going to solve for pressure. Once again, you could think of it like a fraction, if you will. Volume is going to end up on the bottom when it goes to the other side. Dividing it over, P is equal to nRT divided by V. Pop it in our numbers here, 1.82 moles, 0.08206 liters atmosphere, Kelvin mole. Try to squeeze my temperature in there. Kelvin. And divided by our volume here of 5.43 liters. In terms of units, moles will cancel, Kelvin will cancel, liters will cancel. So atmospheres is the only unit that is left at this point, which is good. And if we pop some numbers in a calculator, we'll get an answer perhaps here. And maybe the right answer, we'll see. We end up with a pressure of 9.42 atmospheres in this case. Any questions on that? I would also very common in these problems is you're not given the mole straight up. You're oftentimes given grams. So the use of grams to moles and molar mass is a very common conversion that you also need to do in these problems. In addition, I would say very commonly as well, the volume is usually in milliliters. So a lot of times that milliliters to liters could be something that you have to use a lot with these type of ideal gas models. So a lot of times you will have to take grams to moles using the molar mass and use that 1,000 milliliters equals 1 liter conversion as well. So again, those are two very common. So let's give this one a go here. Calculate the pressure in atmospheres exerted by 32.5 grams of SF6 in a volume of 252 milliliters at 45.5 degrees Celsius. Sulfur there, 3207. Okay, let's take a look. So again, if we kind of pull out the information, we are looking for a pressure here. We got 32.5 grams of SF6. We have a volume of 252 milliliters and a temperature of 45.5 degrees Celsius. And we're obviously looking for a volume. So again, here we pretty much have like a P, a V, a T. Again, here we do not have moles, but obviously we could get from grams to moles really easily. And again, we always have R. So once again, kind of one of everything here should point you in the direction of P equals nRT. Now we just have to make sure everybody's in sort of the proper units. So we obviously here do need to convert our grams into moles. We'll use the molar mass here of SF6 from the periodic table, which looks like 146.07. So 146.07 grams per mole from the periodic table. That's going to give us our moles, 32.5 divided by 146.07. We'll get a 0.2225. Take a couple extra digits. We also need to make sure that our volume here is in liters. Right now it's in milliliters. So we do want to convert that as well. So 252 milliliters, 1,000 milliliters in a liter, going to get us 0.252 liters. And lastly, our last thing here that's not in the right units is our temperature. It needs to be in Kelvin. So we're going to add a 273.15 to it. Got a 318.65. And once again, as previously noted, never usually given to you in problems, but always have the R value available to you, 0.08206 liters, atmosphere, Kelvin, and mole. So now we got, again, everything in the proper units here. So we're going to, once again, solve for P. So we're going to divide our V to the other side, and that will give us our pressure again is nRT divided by V. Popping in our numbers here, 0.225. Our gas constant, 0.08206 liters atmosphere Kelvin a mole. And our 318.65 Kelvin, all divided by our volume of 0.252 liters. Once again, in terms of units, moles will cancel, Kelvin will cancel, liters will cancel. Once again, here leaving us atmospheres, which is our final unit, what we're looking for. So putting in our number, I think I lost me a 2 there. I'm going to pop my 2 in there. So 0.2225 times 0.08206 times 318.65 divided by 0.252. Going to get us a 23.1 atmospheres in terms of our pressure in this case. Any questions on that there? So again, common mistakes people make with the ideal gas law is really the units. Just things aren't in the right units to cancel out correctly. People leave volume in milliliters. They try to use grams instead of moles. So again, those are common sort of issues. Obviously, the normal one as well, temperature, not in Kelvin. All right. So we learned a lot of gas laws at this point, but heck, seems like there's room for more. So let's talk about what happens when we start to actually change maybe pressure, volume, and temperature together. If we actually take the ideal gas law and solve for R, which is a constant, this R here and this R here is the same number, which means you could actually put these two things together and you get a version of this equation, as you can see there, which is P1 V1 over N1 T1 equals P2 V2 over N2 T2. And this is sometimes referred to as the combined gas law. But in most cases, our moles here are really sort of constant and doesn't really change. So really the combined gas law is usually this version of it, P1 V1 over T1 is equal to P2 V2 over T2. And once again here, pressure on both sides does not matter. And it can be any unit as long as you're the same with volume. And like any other gas law, temperature is Kelvin, obviously, as well on both sides. So this is usually the combined gas law that most people roll with. Now, this gas law obviously deals with changes in maybe pressure along the way here and see how everything's adjust. This is probably the best gas law ever to memorize. So this is really the best gas law to memorize. And I'll show you why it is. And it's even maybe best to memorize it with the N in it, just in case. So if you remember sort of the combined gas law, even with the N in it, if you like. and you spend your time just to remember this one little sort of formula here, it could really help you in a lot of situations figure out every other formula that we talked about. So if you remember this gas law and all of a sudden you come across a problem and they don't mention anything about moles, they don't mention anything about temperature, or you're told, hey, they're held constant, all you have to do is come up to this equation, scratch out those two things, and what you're left with is Boyle's law and probably the right equation to use for that formula. If you remember this equation here, and you come across a problem where there is no mention of moles, and or you're told they're held constant, and there's no mention of pressure, you just go to both sides and scratch out pressure and moles on both sides. And now you are left with Charles' law that we learned earlier. If you remember the combined gas law, and you come across a problem that mentions nothing about volume or nothing about moles or they're held constant, just go back and scratch those things out, and you're left with Guy-Lussac's law. Even our good friend Avogadro can be helpful here. If you come across a problem and it mentions nothing about pressure and it mentions nothing about temperature or they're held constant, you get rid of pressure and temperature on both sides. And now you have Avogadro's law. And if you remember PV equals nRT and the combined gas law, and if you want to remember it with or without the n, you'll be in good shape in most cases. You pretty much could get to every other gas law that we just used, learn that you have to memorize anyways. And if you cross out what's held constant or what's not mentioned, you'll be left with pretty much the equation you should probably be using for that problem. So this is probably the best one to memorize. I don't know how much Avogadro's law you're going to come across in your life. So if you want to just do the P1 V1 over T1, you'll probably be good for most of the ones. But if you want to leave the n in there as well, if you want to leave the n in there as well, that will also help you remember PV equals nRT, because basically either side of that P1 V1 over N1 T1 equals R. So it also gets you the ideal gas law as well. So if you're one, all you have to remember is now you basically have the ideal gas law sort of rear well. So that's a really good gas law to remember because of all the other gas laws. All right, let's try one here. We have a sample of oxygen gas at 27 degrees Celsius with a volume of 9.55 liters and pressure of 2.97 atmospheres. We change the pressure to 8.25 atmospheres and we keep it up to 120. Okay, so let's take a look. And again, if we pull out the information here, we got a temperature at 27 degrees Celsius. We have a volume of 9.55 liters, and we have a pressure of 2.97 atmospheres. We have another pressure of 8.25 atmospheres, and we have a temperature there of 125 degrees Celsius, and we are looking for a volume. So once again, like I was mentioning a second ago, if you maybe just invest your time to learn that equation right there, all you have to do is go, I got some P's, some V's, some T's. I don't see anything about moles or grams. So all I have to do is just scratch out the moles on each side. And now I have pretty much the combined gas law, which is the one that I want to use here. So again, you can use this. We do want to make sure everybody's in the right units. In this case, both pressures are in atmospheres, so that's good. In terms of our volume, it is in liters, and that's okay because our answer will just be in liters when we solve for it. But once again, here our temperature does need some converting, so we'll add our 273.15, and that's going to give us 300.15 Kelvin. and also T73.15 on this side, 398.15 Kelvin. We now have everything we need. We now have our right gas law here, our combined gas law, which you could kind of see. And you could call these guys the ones, call these guys the twos. And in this particular case, we are solving for V2. So once again, people do sometimes struggle rearranging these equations. And again, if you just want to do it the easy way, when you go across the equal sign, they end up in the opposite location. So the T2's on the bottom, it will end up on top. The P2's on top, it will end up on the bottom. And if you do that, you will end up with P1 V1 T2 divided by T1 P2 is equal to V2 in this case. Obviously, whatever we're solving for should always be on top by itself. Yeah, otherwise it's on the bottom. You're doing the inverse of it, so you got to make sure it's. Now we can put everybody in the right spot, hopefully. So we're going with P1, which is 2.97, B1, which is 9.55 liters, and T2 up on top, 398.15 Kelvin, all divided by there are T1, which is 300.15 Kelvin, and RP2, which is 8.25 atmosphere. Again, atmospheres will cancel, Kelvin will cancel, going to leave us lead. And 2.97 times 9.55 times 398.15 divided by 300.15 and divided by 0.25. Gonna get us a 4.56 liters, looks like, perhaps. I punched in all those numbers correctly, hopefully. Any questions? If you just have just the volume and temperature and you want to calculate pressure, um, you would need something to do with moles somewhere along the way, I would think. You would need something. So if you have just volume and temperature, you have two volumes, two temperatures. Well, we can look at it afterwards if you want to come up and take a look at it. Other questions? Okay. All right, that's what I just did. All right, so the next thing we're going to talk about is stoichiometry involving gases. And we've done sort of traditional stoichiometry with grams and moles. And here with stoichiometry, the good news is it really does really work the same way as the stoichiometry we talked about previously. You will follow those same steps. You'll balance the equation. You will convert to moles. If it is a limiting reagent problem, you need to also figure out the limiting reagent like we talked about. Then you'll do your mole to mole relationship. And then you'll do your moles to some other unit. Now, what makes gas stoichiometry different than a regular stoichiometry problem is, I would say in most cases, 99% of the time, not more, you'll get an ideal gas law somewhere. So somewhere along the way, you'll use an ideal gas law in most cases, not in all cases, but in most cases. And I would say most commonly at the very end here, you would be solving for volume as a very common sort of ending. So you use sort of the moles at the end of your stoichiometry problem, stick it in the ideal gas law. Another possible place that you could use sort of a gas law in your stoichiometry problem is at step number 2. And at step number 2, when you convert things into moles, you can use the ideal gas law and solve for moles, which would be PV over RT. I would say very commonly, probably the ending move here is very common, but you can also, again, using moles, you can use the ideal gas law. and convert to moles, and then kind of do the rest of it together. I would say in a lot of cases, you might not have too many limiting reagent problems involved. So most of it will be probably a basic geometry type of way, or steps, not has to worry about reagent. Again, it's always possible with any type of stoichiometry problem that it could be a limiting reagent situation, but I would say in most cases, probably going to be more of a basic stoichiometry problem with gases. But again, you kind of have to incorporate that gas law somewhere along the way. So for example here, if we take a look at this equation here in this problem, we're interested in what volume of CO2 is produced at 37 degrees Celsius, 1 atmosphere, when we have 5.6 grams of glucose is used up. So if we think about what's going on here, we are given that we have 5.6 grams of glucose. We are interested in the volume here of our CO2, which is a gas. So because of that as well, we do have a temperature associated with it, 37 degrees Celsius. And we also have a pressure associated that's going on here. So if we think about the CO2, which is a gas, and we think about our PV equals nRT, we do have the temperature, we do have the pressure, we always have R. So once again, R is always available to us, even though usually never given in a problem. So really the only thing we're missing to allow us to solve for pressure for the CO2 is the mole. And that's going to come really from the stoichiometry part. So in this case, we're actually going to use stoichiometry to figure out how many moles of this gas we would produce. And then we can use the actual gas law to figure out how much volume that would represent under these conditions. So really, in this case, we're just going to start it like a basic stoichiometry problem. We're going to balance the equation, which is done already, thank goodness. We're going to take really whatever they gave us and convert it into moles, and we do need to do this. By the way, I also know that this is not a limiting reagent problem because I have no information about this guy here. So there's no way I could get the moles of that guy. And remember, for it to be a limiting reagent problem, I have to get the moles of each reactant in this case. So it's just a basic. So we're going to get the molar mass here, C6H12O6. So we got 6 times 12.01 plus 12 times 1.008 plus 6 times 16. And we're going to convert into moles. So we're going to take what they gave us, 5.6 grams, C6H12O6. Going to use the molar mass from the periodic table, which is 180.2 grams per mole of C6H12O6. If I were to stop right at this point, my grams of glucose is going to cancel, and I'm going to be in moles. Problem, though, is in the particular problem, I'm not interested in moles of glucose. I'm interested in the moles of the CO2. And this is really the third step of stoichiometry, right? We're going to use the equation to get to the moles of CO2. If you want to get an answer at this point, you can, but I'm just going to kind of continue on the calculation. And I'm going to now go from moles of glucose to moles of CO2. And from the equation, it's a 1 to 6 relationship. So for every 1 mole of glucose, I get 6 moles of CO2. And that really would be like our third step in stoichiometry here. So we'll take 5.6 divided by 180.2, gets you about 0.031. And we're going to times it by 6. And we're going to end up with 0.186 moles of CO2. Once again, I needed that to figure out what's going on here with my CO2 and the ideal gas law. I now have everything I need except for our normal, which is my temperature needs to be converted to Kelvin. So we're going to convert that to Kelvin because we are going to use the ideal gas law here. So we're going to go 37 plus 273.15. Going to go 310.15 Kelvin. I can now really do the fourth step of my stoichiometry, which is we're going to use the ideal gas law. Once again, here we're interested in volume. So we're going to solve for V. We're going to bring P to the other side. Volume will equal nRT divided by P in this case. Popping in our numbers for CO2, we will end up with 0.186 moles. Our gas constant, 0.8206. Our temperature converted to Kelvin because we are using the ideal gas law, and all divided by our pressure, which I think was 1 atmosphere in this case. Atmospheres will cancel, Kelvin will cancel, moles will cancel, going to leave us liters as a unit, which is good because we are looking for a volume. And that's going to get us a 4.73 liters of CO2 in this case. And again, it is really the same for stoichiometry steps, except for very commonly, like we did here, we kind of use the ideal gas law at the end. So instead of taking the moles at the end and getting grams, we're going to figure out the volume using the gas law. So, by the way, when we look at this number of 4.73 liters, that is a product. That is the theoretical yield in this reaction, right? As we just saw there, we could do our same really basic 4 steps with stoichiometry. Again, like I said, somewhere along the way, you may need to use an ideal gas law, or maybe even twice, or some type of gas law maybe at the end. Sometimes as well, at the end, you may even use like the combined gas law as well. So let's take a look at another one here and see what you come up with. So considering this reaction here, what volume of hydrogen gas at 27 degrees Celsius and 1.25 atmospheres is required to react with 5.65 grams of phosphorus. And phosphorus is 3097 here. Problem definitely involving gases since we're looking for a volume of hydrogen gas. So if we just think again about the hydrogen gas, which obviously is our gas here, we could also think about P equals nRT if we need to use it. We're looking for a volume. We do have a temperature, which is 27 degrees Celsius. We do have a pressure, which is associated with the gas, 1.25 atmospheres. Again, remember, we always have R, 0.08206. So again, if we kind of look at our ideal gas law, we do have basically T, we have R. We're looking for a volume, and we do have pressure. So once again, we are going to use here stoichiometry to figure out the moles of the hydrogen gas. So really the only other piece of information we have in this problem is how many grams of phosphorus we're starting with. And again, that's really where the stoichiometry is going to come into play. We're going to use that to basically use stoichiometry to go from phosphorus to hydrogen. And we'll just start our steps here. So balanced equation we have. We do need to convert into moles. So second step here, we're going to take our 5.65 grams of P4. We're going to go to the periodic table and convert our molar mass. So that's 4 times 3057. That's going to be 123. Again, we do want the grams on the bottom, so everything cancels. Moles of P4. Once again, here you could get an answer, but I'm not going to because I don't really want more interested in the gas. Again, that's the third stoichiometry. Now going to use our multiple to go from phosphorus between the two reactants. So we will do from the equation 1 mole of P4 will give us 6 moles of H2. Ultimately, where we want to kind of end up here with our calculation with moles of H2, because that's the gas we're looking to figure out the volume of. We're going to divide it by 129. That's not that. Try that here. 560 times 6 divided by 123.9. That's going to get us 0.2736 moles of hydrogen gas in this. That again is really kind of the missing piece that we need here to do our ideal gas law. So we could do our ideal gas law with really the 4th step here, P equals nRT. We're going to solve for volume. We can divide that to the other side. Volume will be nRT divided by P. Once again, this is the ideal gas law, so we want to make sure everybody's in the proper units. So our pressures and atmospheres, and surprisingly enough, our temperature needs to rise a little bit. 3.15. That's going to convert our temperature here into 300.15 Kelvin. And now we have everything in the proper units. So we'll take our moles we calculated through stoichiometry of our hydrogen gas. We'll use our gas constant here. We'll use our temperature that converted to Kelvin, so we pop it out, divided by our pressure, which would point to atmospheres. Once again, atmospheres will cancel, Kelvin will cancel, moles will cancel. It's going to leave us as liters as the over here. And we will end up with 0.2736 times 0.08206 times 300.15 divided by 1.25. It looks like we will end up with 5.39 liters of H2 in this case. Question on those calculations. Again, you can see it is really just four sort of stoichiometry steps with sort of the gas law thrown in as well. By the way, also a reminder that it is not a yield, as that's a reactant, right? So it's not a product or anything like that. So it's just with it. Let's take a look at one more maybe here, similar to what we'll be doing tomorrow. All right. So magnesium reacts with hydrochloric acid to produce through this reaction that we'll see tomorrow. Calculate the volume of hydrogen gas produced at STP if you react 5 grams of magnesium with excess HCl. Magnesium 2431 there. Periodic table. All right, let's see a few moments there, see what you come up with. Okay, so let's take a look, see how you're doing. Here we want to calculate the volume of hydrogen gas. Once again, that is a gas here. So again, maybe bring up some PV equals nRT possibilities. Here we're looking again for the volume. We are produced at STP. Remember that STP does stand for a temperature and a pressure. So the temperature here, if it was STP 273.15 Kelvin, pressure here is going to be 1 atmosphere. So again, that is basically what P stands for. Again, if we're going to go the ideal gas route here, we always have our 0.08206. So much like we've been seeing, in order to find volume here, we are missing moles. And again, that is where the geometry is going to come into play here. We're going to start with our only piece of information that's on the left, which is we have 5 grams of magnesium. We're once again going to use magnesium to figure out how much hydrogen moles we're going to produce in this case. So step 1 is a balance equation, which we got. Step 2, we're going to convert our information into moles. So 5 grams of magnesium, molar mass here of magnesium, 2431 grams per mole. Once again, much like in the other examples, if we stopped right here, we would be in moles of magnesium, but we are ultimately interested in hydrogen in this case. So we're going to do the third step, which is our mole-to-mole relationship. And from the equation, for every 1 mole of magnesium, that will get you 1 mole of hydrogen. Moles of magnesium will cancel. So ultimately here we're taking 5 really divided by 2431 here. And that's going to get us 0.2057 moles of hydrogen. That again is sort of the missing piece that we need if we're going to use the ideal gas law here. So once again, we are solving for volume. So our PV equals nRT. Our volume will be nRT divided by P. Again, bringing that to the other side. So the volume in this case are moles, 0.2057. Our 0.08206, which is our gas constant, our temperature at STP, 273.15 Kelvin, all divided by our pressure at STP, 1 atmosphere. Atmospheres cancel, Kelvin cancel, moles cancel, here leaving us with liters left over. So 0.2057 times 0.08206 times 273.15. Gonna get us 4.61 liters of H2. This would be a theoretical yield in this case, as hydrogen in this example is a product. And what we're actually looking to try to figure out. First off, any questions on that calculation there? Yeah. That's exactly what I was just going to say. In this particular case, you did have an option to do it a different way without the ideal gas law. And that is because in this situation, we are at STP. And because we are at STP, you could absolutely use that conversion that 1 mole is equal to 22.414 liters. And you can really bypass the ideal gas law at this point if you wanted to. You would just need to pick your moles up from here and basically use that as a conversion. And again, we could only use this at STP conditions, which we are in this problem here. So you could do 22.414 liters. Moles will cancel. You'll end up with the exact same answers. So you do have, again, both options in this case because it is STP. Again, a friendly reminder that if it is not STP, you should not use it. But in this case, it is appropriate. And as you see, if you could recognize that it is a situation, it could save you a little time and you kind of eliminate kind of doing the ideal gap. But again, if you want to be safe and not have to worry about using it in the wrong situation, like I said earlier, you could always go into the ideal gas law no matter what the situation is. Other questions? All right. We'll be doing that tomorrow. All right, so that's gas stoichiometry. Once again, pretty much same steps. Involves really some type of gas law along the way. The next thing we're going to talk about is what's known as Dalton's law of partial pressures. And sounds really difficult, but not too bad. So a lot of times what happens with gases is it does sort of come as a mixture of gases, or a lot of times you do have a mixture of different gases. And partial pressure is the idea that each of the gases, which is the mixture, is contributing partially to the overall pressure of what's going on. And that is basically what Dalton's law of partial pressure is. So a very simple explanation here is this. If I had a container where only I had gas molecule A's flying around, the total pressure of that situation is all basically gas A, the pressure of gas A. But if I had a container where we had gas A flying around, gas B flying around, gas C flying around, the total pressure in this situation is the pressure of A plus the pressure of B and the pressure of C gas. These are all contributing to the overall pressure, and these are all what are known as partial pressures. Yeah. So that would be the partial pressure of A and the partial pressure of B. So they all contributing to them. Now, one of the nice things about this is, again, we usually assume ideal gas behavior, which means that even though all those basically assume that they are in there by themselves. So we don't have to really worry about any contribution from gas. Yeah. And that gives us our partial pressure here. So how do we basically figure out partial pressures? Well, I'll be honest with you, probably the most common way you do that is the ideal gas law, P equals nRT, and you solve the ideal gas law for pressure. Gas. So this was pressure for A, partial pressure of A, partial pressure of B, nRT over V. And that's probably common to calculate pressure. Now, one of the good things about this is if you have a mixture like we do over here, where both of those gas molecules are together, there are a couple of things that are the same for everybody. Because they're in the same container, everybody here will have the same volume. So for every gas that's floating around in there, they're all in the same volume. And probably that container is sitting in the same location, and that means that they will also have the same temperature as well. So what ends up happening when you're calculating part of the volume is going to be the same for everybody. R is a constant, which means it's going to be the same for everybody. Calculation partial for each gas in the mole. So figure out the mole of each gas you got in there. Basically, that's the gas law individually for each gas. Not there. And by the way, as many gases as you got floating around, you basically could just do that. Now you will do the ideal gas law sort of individually for each pressure or each gas. And to find the total pressure, all you have to do is simply get whatever the pressure of gas A is, you add the gas to float around in there, and that will give you the total pressure. So why don't we try one here? Let's say you have 5 grams of helium and you got 5 grams of neon in a 2.5 liter container at 27 degrees. We want the partial pressures of each gas and what the total pressure is. Helium 4.003 and neon 2018, I believe. So we're looking for 3 things here: partial pressure of helium, partial pressure of neon, and the total pressure of both these guys together as they are floating around in this container. You got helium, you got neon floating around. Okay, so let's take a look. So again, we have in this situation a mixture of helium and neon flying around in the same container. So once again, the temperature is going to be the same for both of them, 27 degrees Celsius. They are both in the same container, so 2.5 liters is going to work for both of them. And really, for the most part, partial pressures, again, it's really just an ideal gas law problem that you're just going to do for each gas individually. Now, that means we're basically going to go PV equals nRT for each gas. We're going to solve for pressure nRT divided by V. We have obviously the volume, the temperature for each gas. We always, again, have R available to us, which is our 0.08206. And that means, as we talked about, really the kind of thing that we need to kind of figure out is the moles. We also do need to convert our temperature into Kelvin, kind of like normal, so might as well do that as well. So that's going to give us 300.15 Kelvin. Now, one of the reasons why we cannot do an individual calculation of each gas, even though they are flying around the same container, is really the idea of it being an ideal gas. So again, one of the things that makes something an ideal gas is even though there may be multiple gases in the same container, they essentially don't interact with each other. And you could almost think of them as being in there by themselves. So that's why we could almost apply, this sort of individual look at them like they were in there by themselves, even though there are different gas molecules there. So I'm going to start with converting each of our grams into moles. So we'll take our 5 grams of magnesium. We'll use not magnesium, how about helium? It's kind of like magnesium. Not so much. I'll try again. 5 grams of helium, using the molar mass of helium, 4.003 grams per mole. That's going to get us here 1.25 moles of helium, we'll call it. We'll do the same thing for our 5 grams of neon. Divide by the molar mass from the periodic table of neon, 2018 grams per mole. And that's going to get us here about 0.248 moles of neon. We basically now have everything we need for each gas to find the partial pressures. So starting with helium, the partial pressure of helium, again, will be nRT divided by V. Popping in our numbers for helium, 1.25 moles, 0.08206 for our gas constant, our temperature, 300.15 Kelvin, and our volume here of 2.5 liters. It was in liters, so that is good. Liters cancel, moles cancel, Kelvin cancel. Going to leave us atmospheres here, and they're going to end up with about 12.3 atmospheres in this case. And that would be the partial pressure of helium in this case. We're going to basically just redo the exact same calculation here. The only thing that's going to change is the moles in this case. So we'll use the moles of neon, but pretty identical, exactly same calculation. And using the moles of neon, 0.248 moles. Again, our gas constant. Because they're in the same container, still the same temperature, and because they're in the same container, still the same volume as well. Once again, liters cancel, Kelvin cancel, moles cancel, leaves us our atmospheres left over. And it looks like we're going to end up with about 2.44 atmospheres. And that would be known as the partial pressure of neon in this case. First off, any questions on those calculations? So the last thing we're looking for is the total pressure of this mixture, and that is basically just found by adding each of the partial pressures together. So the total pressure in this situation will be the partial pressure of helium that's flying around and the partial pressure of neon, and that would be a 12.3 plus 2.44 atmospheres, giving us a 14.7, I believe, as our total pressure in this particular case. Any questions on that there? We can see in this particular case, it is helium that is contributing more pressure. Any ideas why helium is contributing more pressure? It has to do with the molar mass of helium. Helium is like 4 grams. Neon is 20 grams. So helium is lighter, which means it's going to have a faster velocity and flying around faster and going to cause more collisions. And that's why we see helium is actually contributing a lot more pressure because it's light, moving faster than the heavier, slower moving neon in this particular case. Any questions on that there? We're going to skip that, I think, here. So let's talk about another sort of partial pressure situation. And this is a situation that occurs when we collect gas. And in certain cases, we collect gas kind of like in this setup here, which is an experiment we used to do, but we don't do it anymore. But if you take some potassium chlorate here in this case, and you basically heat it, it is going to go through a decomposition reaction to produce some potassium chloride. It's actually going to be solid. And some oxygen gas in this case. And this is a solid. We'll do a little balancing here. I guess like I'm in chemistry class, we'll do a little 2 there, maybe a 2 there. And I feel like maybe a 3 there. There you go. And in the thumbs up. That's good. I did not bad. I can maybe pass the class. We'll see. So as we heat this up, this potassium chlorate is going to go through a decomposition. It is going to produce some oxygen gas in here, which obviously has nowhere to go but to travel this way. It will travel out the tube here, which is now underwater, and in this receiving container over here, which was full of water to begin with. So as the gas comes in, it will actually displace the water that's in there. Very similar to what we're going to do in tomorrow's experiment. When you make the hydrogen gas, you're going to displace the water in your tube. Water will go out, gas will go in, and you'll end up with what appears to be in the receiving sort of container, an empty spot. Kind of looks empty. But it's really not empty because that is where all your gas ended up. So in this case, this is where all the oxygen gas basically ended up in this sort of process. Now, as a consequence of collecting the gas this way, where we kind of displace water, usually if we do some type of reaction with involving water and some heat, usually some of that water will then become not liquid water, but will actually come as steam or vapor, basically. And the consequence of collecting a gas in this situation is, in addition to the gas you're actually interested in, you will pick up some extra gas, which is water vapor. So you'll pick up some water vapor in this case. The problem with that is you're not really interested in the water vapor. You're actually interested in the oxygen gas. It's almost like a contaminant, if you will, as through the process of how you collect it. We will have that same situation tomorrow when we collect the gas. We're going to displace the water. So in addition to our hydrogen gas tomorrow, we will pick up some water vapor along the way in the actual spot there. So this brings up a partial pressure situation where the total pressure of this mixture is the pressure of the gas you're collecting, plus the vapor pressure of water is what this is sometimes referred to, the vapor pressure of water. The good news is that in most cases is a table value, or somewhere you can look up in a table based on temperature. So you can look up the temperature of what you're reacting at, and you can find the vapor pressure of water. A very common situation is we sort of do a correction. The good news on this one is it's pretty much just subtraction. So usually it's a pretty good deal. We take the total pressure, which, by the way, when you do an experiment, is typically the barometer reading that you would do. So you typically would take a barometer reading that gives you the atmospheric pressure. And basically, we're interested in the partial pressure of, let's just use this example here. We're actually interested in the oxygen. So the partial pressure of oxygen would equal the total pressure minus the pressure of the water vapor. And you could kind of think of this almost like a correction sort of value or calculation. And very commonly, people, when they do experiments, will also write this as the pressure of the dry oxygen gas, because you're kind of subtracting off water vapor's contribution to the pressure. So in the lab tomorrow, you'll also probably see somewhere it will say the pressure of the dry hydrogen gas or something like that. And that is through a calculation like this, which is basically just subtracting. So usually, like I said, you kind of find that value on a table, you subtract that value from the atmospheric pressure, and that'll get you the pressure of really the gas you're interested in. Because again, if you're doing this experiment, you're interested in the oxygen gas. You're not really interested in the water vapor that you collect. It is sort of a byproduct of how you collected the gas. Here's a table from your book, again, of some vapor pressures. And again, you would usually reference this, and obviously it would be provided to you if you needed it in a problem. But you usually will have to kind of reference it. Usually it's not going to be given to you in a homework problem or anything like that. So you may have to reference this table, you know, to solve some problems, stuff like that. On an exam or quiz, obviously that stuff would be given to you. All right, so why don't we try one here? A sample of oxygen gas is saturated with water vapor at 30 degrees Celsius. The total pressure is 753 torr. The vapor pressure of water at 30 degrees is 31.824 torr. What is the partial pressure of oxygen in atmospheres? So take a few minutes here and see what you come up with. Okay, so this is basically the situation that we just saw there in that picture. How do you know if you're just reading a problem that it is this situation? A lot of times there'll be some words in the problem that will kind of point you in that direction. And in this particular problem, it is these words here, saturated with water vapor. So if you see something that says something like saturated with water vapor, or it says, hey, you collected the gas over water is another very common way sometimes it's worded, collecting the gas over water, saturated with water vapor, something to do with water a lot of times, and how you're collecting the gas, an indication that kind of correction calculation that you need. So what we know in this case is the total pressure will equal the pressure of the oxygen gas plus the vapor pressure of water. As basically in this situation, we're collecting both of these guys. Now we do have the total pressure given to us, which was 753 torr. We are interested in just the oxygen gas. Now, the vapor pressure of water was also given to us in this problem. I will say sometimes, or a lot of times in maybe book problems, they won't actually give it to you in the actual problem. You have to go to that table and kind of look it up and stuff like that. But again, in this situation, you would go to that table, find 30 degrees, and find the vapor pressure of water is basically what you would find. And if you did, you would find what we have here, hopefully, 31.824 torr. So again, basically our pressure of oxygen gas, or our dry oxygen gas in this case, would be 753 torr minus 31.824 torr. And we'll go 753 minus 34.824, about 721 torr. We do want it in atmospheres, so remember that is our 760 conversion. 760 torr is an atmosphere. So we'll divide it by 760, and we'll end up with 0.949 perhaps as our partial pressure of oxygen in this case. And again, very commonly sometimes referred to as the dry pressure of dry oxygen. Questions on that there. So this is again a very common sort of conversion factor or correction calculation that's done with gases the way they're collected. By the way, you could also use this formula, and obviously, which is the previous formula as well. If you are given the total pressure, maybe a couple partial pressures of some gases, and you just want to find the other partial pressure, all you have to do is subtract and figure out what the missing partial pressure is without having to use ideal gas law. So sometimes you may come across a problem that go, hey, the total pressure is 750, pressure of hydrogen is this, the pressure of oxygen is this, what's the pressure of nitrogen, that mixture? Again, basically it's just a subtraction problem at that point. You just basically subtract them all. Any question? So we're going to talk here at the end here about the kinetic molecular theory gases. A lot of this we've sort of touched upon. You do need to know sort of the main parts here. Gases consist of tiny particles, atoms, or molecules. These particles are small compared to the distances between them. So the volume of the individual gas molecules can be assumed to be negligible or zero. That, again, as we've been talking about, is one of the things that makes something an ideal gas, is that idea that the volume of the gas is small and the volume is flying around in. So it's more important about the volume it's flying around in. Again, in an ideal situation, you can think of it like the trash can there, and like, the gas molecules are very, very small, like marble or something in there. Much bigger volume that's flying around in than the volume that's taken up itself. As I mentioned before, when you get to real gases or non-ideal gases, you do actually have to take that into size. What happens in a real gas situation is, instead of it being a small marble in that trash can, it's like a basketball in that trash can. So it does very important the volume of the gas molecule itself. Particles are in constant motion. Again, as we've been talking about, it is these collisions that causes the pressure we associate with gases. Now, the number 4 here is really the other main thing that makes something an ideal gas. And again, that is the idea that particles are assumed not to be attracted to one another, even one another. So this again is why in the problems we just did with the partial pressures, that even though there was multiple gases flying around in the same sort of container, we could almost do the calculation based on them just being there by themselves, and there was no other people involved because they're not going to really interact with each other. Why is that important? Let's just say you were in a non-ideal gas situation and you have this gas molecule. And if you had the same gas molecule in an ideal situation, it's going to have no problem like hitting the wall. But if you had it in a non-ideal situation and there was another gas molecule, maybe these guys are now attracted to each other, and that will slow this guy down, perhaps, from hitting the wall as quickly. Away. Could also do the opposite. It could like I don't want to be around way really faster and cause maybe more collisions. So in a non-ideal situation, when there is sort of attraction and forces happening, you do have to take those into account. As I mentioned earlier, it kind of turns the ideal gas law into a scary looking equation known as the van der Waals equation. Lastly here, the kinetic energy of gases is directly proportional to the Kelvin temperature. And typically, if the temperature increases, we typically do see the gas molecules moving faster. And if they are decreasing in temperature, it typically will kind of slow down. So some of the relationships that we talked about here in this chapter, again, temperature is the measure of motions of the gas. Higher temperatures, as I just mentioned, they're going to be moving faster. Probably would expect more collisions happening, and that should definitely affect the pressure. At lower temperatures, they will be moving around slower and will have less collisions occurring. The relationship between pressure and temperature, that sort of Guy-Lussac's relationship, that if the volume does not adjust, if you increase the temperature, again, that's definitely going to lead to more collisions, with by result of that will lead to higher pressure. And if you lower the temperature, less collisions going to see a drop in the pressure. When we do have a situation where we can adjust the volume like we did with Charles' law, that volume again will adjust to allow us to maintain constant pressure. So when we increase the temperature in a Charles' law situation at the bottom there, we do expect the volume to increase as well to maintain the number of collisions and the pressure, and vice versa. If we lower the temperature, we're going to drop the volume to maintain those collisions and keep sure where they're at. Any questions on any of that there? That is chapter 13. Any questions? All right, we're going to do a little bit of 14. Seems like a good about liquids and solids. Not too big of a chapter. I guess final exam material, I guess is what that would. Yeah, the exam will go up through 13, which we just finished, the gases. So liquids and solids. We're going to tie into some stuff that we talked about in an earlier chapter, which was chapter 10, a little specific heat and energy. And we talked about some phase changes that occur going on here with liquids. We'll also talk about how, I believe in this chapter, how things interact with one another through intermolecular forces officially. So let's talk a little bit about water. Water obviously is colorless, tasteless, and one atmosphere, it will freeze at 0 degrees Celsius, and the normal boiling point of water right is 100 degrees Celsius. We have basically liquid water happening between 0 and 100 degrees. Is not to get a little bit below 0 degrees that you do sort of transition into ice, not until you're above 100 degrees that you transition into gas. At exactly 0 degrees or exactly 100 degrees, I'm really it's half time. 0 degrees Celsius, you have ice water happening, and you got ice crystal swallowed, you got some liquid water happening. And again, at 100 degrees, you got a little bit of liquid and some gas sort of happening at the same time. Some important properties of water that we talked about as well along the way. Water density in the liquid thing is 1 gram per milliliter. Remember, it does change with temperature density, but that's usually the value that you use if you ever need sort of the density of liquid water. One of the unusual sort of properties of water, as we probably mentioned in an earlier chapter, is in this phase, as you can see there, the grams per milliliter. And that is, as we'll talk about, and maybe I've talked about previously, in the sort of solid phase, when these water molecules basically come together, they don't have enough energy to get really, really close to one another. And essentially, what ends up happening is it creates a lot of volume or space between the water molecules in the ice form phase. And as you remember, density, right? Mass divided by volume. So we'll kind of have open volume between water molecules, kind of bloat the volume part of that calculation. And bigger number on the bottom divided by smaller number on the top gives us a smaller value for density. And our density value does decrease down there. And that's very unusual. Most things are more dense in a solid state than in a liquid state. And that's because, again, water is also held together, as we'll talk about, by very strong sort of hydrogen bonding. So, with a lack of energy and the strong hydrogen bonding, they kind of keep their distance in the solid phase. Oddly, in the liquid phase, they have a little bit more energy, so they're able to kind of overcome that a little bit and get actually closer to one another. And that makes it have a greater density there in the liquid phase. This is a heating and cooling curve for water. And when we look at this curve, we have ice, which is obviously our solid state of matter. We have obviously here our liquid water, which is our liquid state. And up here we have steam, which is obviously our gas sort of phase there for water. And we have our normal sort of melting points and freezing points. So right here at 0 degrees, our melting point, freezing point. And right here at 100 degrees, it's our normal boiling point. And as you can see from this particular, at those areas, when we are changing phases as we go from solid to liquid or liquid back to solid, or even liquid to gas or gas back to liquid, we are not changing the temperature. So that again occurs at the same temperature. What you're doing in terms of the solid state, apply energy and in an endothermic process, the ice gains energy, will transition to liquid phase. If you're at like 0 degrees and you're in the liquid phase and you remove energy and an exothermic process for the liquid water, it will then become solid ice phase. So it all depends at the sort of spot, the boiling point or the melting point, what you're doing with energy. And when we talk about energy, there is a certain amount of energy that's required to do nothing more than change the phase of a substance. So one of it is known as the heat of fusion. And the heat of fusion is another thing that we saw earlier. It is sometimes referred to as a delta H of fusion. And if you remember our energy chapter there, change. But the delta H of fusion is the energy required nothing more than take a substance at its normal freezing point or melting point from solid to liquid or liquid back to solid. It has nothing to do with changing the temperature of that substance or anything like that. It is simply just doing that transition. That is, if we come back here and look at this graph, that is what is happening here on the flat line. That is our delta H of fusion happening there, flat part of that graph. That is the energy to go either way. Again, solid to liquid or liquid back to solid. Now for water, the delta H of fusion is 2 kilojoules per mole. That is roughly 335 joules per gram. And that is, by the way, specific for water. So when we see if you were talking about some other substance, it would have a different heat of fusion. It would also, by the way, have a different melting point, freezing point temperature. It may not be 0. So 0, when we talk about, is specific for water. So is this number? Well, Just like we talked about, as you go from, for example, solid to liquid, that is an endothermic process. And when we talk about energy, endothermic values for energy usually are positive values. And that would mean you would need like plus 335 joules per gram for water to go in that direction. As we go from liquid back to solid, you have to release the energy, which is an process on the energy chapter. That is a negative number. The number is actually the same, but the sign is different to indicate that it's being released. And that would be negative for water, 335 joules per gram. So the heat of fusion is the same regardless of what you're filling. Just like we talked about with energy, we oftentimes use the negative or positive version of it to indicate on or an extra process going on. Question. Now, just like there's an amount of energy required to change the phase of a substance at its normal melting point and freezing point, there's also an amount of heat required to change a substance from liquid to gas or gas back to liquid at its normal boiling point. And at its normal boiling point, where this occurs, up here, by the way, is our melting point, freezing point. And that is what is known as the heat of vaporization, sometimes abbreviated as delta H of vaporization. So delta H of vaporization, vape, the abbreviation for the heat of vaporization. That again is the energy required to not change the temperature of the substance, but once again, simply take it, in this case, from liquid to gas or gas back to liquid. And for water, it's roughly 40.6 kilojoules per mole, depending on your book, maybe 43. And that roughly is about 2,260 joules per gram is the energy required, again, specifically from the gas or gas back. And at the solid to liquid transition, as you're going from liquid to gas, that is an endothermic process, positive 2260 going in that direction. If you're going from gas back to liquid, that's exothermic, minus 2260 going in the opposite direction. And if we take a look at the sort of graph there, that is what is happening right here at this flat line at the boiling point. That is the delta H of vaporization happening. I'll get rid of some of these things here so we can kind of see it maybe. So right here, delta H of vaporization, right there, delta H of fusion. First off, any questions out there? Now, if you look at this graph, it is a heating curve going from bottom to top because we're going from ice to liquid gas. It is a cooling curve going from top to bottom, gas to liquid to ice. Now, if you look at this graph, we do see some points on this graph where it is not a flat line. And it is basically, I'll use this. Try that one. This is kind of going upwards. This is also going upwards. And that is also going upwards. Now, everywhere I highlighted, there are two things happening. So, for example, in this area that I highlighted, that entire area is the liquid phase. And the thing that is changing is as it increases there, the temperature is changing. So we have something that is the same phase, but the temperature is changing. And believe it or not, we actually have already done that. Specific heat, Q is equal to ms delta T. Remember, the specific heat capacity of liquid water is that 4.184 number per gram per degree. So when you look at this graph, anywhere in this region here, if you wanted to figure out how much energy is required to do that, you got to throw down the old equation there, Q is equal to ms delta T. Take it over here, a little specific heat equation, and down here in the ice region, specific heat equation is needed. So if you look at the graph and you're sort of keeping track of what's happening, you're going but the phase stays the same, that's a specific heat calculation. If you're anywhere where the temperature stays the same, but the phase changes, and you're doing either a heat of fusion or a heat of vaporization calculation. Now, also a reminder, especially in this chapter, because it's time. I was down in this area here where this is ice. This way, this is all ice. It is changing temperature, but it's all the same phase all the way through there. When I go to use my Q is equal to ms delta T, I go for S for water. This right here is not 4.184 because that is ice, which is water in the solid phase. It is a specific heat capacity of about 2. We'll call it 2.09 joules per gram per degree Celsius. That is actually for ice. Same thing if I was up here. Up here is all the same phase. That is all steam. That also is not liquid water, which is 4.184. That is steam, and you would want to use a specific heat capacity for steam, which oddly is also about 2 grams per degree Celsius. So definitely in these types of where it's also very common error sometimes people make is they roll with that 4.18 for the piece of way. Again, that 4.184 is liquid water. You happen to be in the ice region of this graph or of this graph, and you need to use the specific heat capacity. You want the right number. So that's a common thing. Any questions on that there? So let's take a look at one here of how we kind of put all this together. And before we do, we could also see something that we do see on the graph, but we need to see the number. We do see here that it takes a lot more energy to do the transition to gas. 100 or so there for water than it does to do the transition from solid to liquid, which is only about 335 joules. And that is because if you think about it, as you go from solid to liquid, things are still relatively close to one another, right? But as you do the transition from liquid to gas, things are completely breaking apart from one another, go into the gas phase, they're completely separating apart from one another. And that requires a lot more energy to get everybody away from one another. And that is why it takes a lot more energy to go from, again, liquid to gas than it does to go from solid to liquid, where they still are moving away, but they're still relatively close to each other. That's why it's not energy. Once again, as I mentioned earlier, the again are specifically for liquid water or water. If you're dealing with some other substance, you would have different values for them, and also different melting points and boiling points and freezing points for those other substances. So let's say we're going to do this problem here, and we want to know how much energy is required to change 75 grams of ice at minus 3.5 degrees Celsius, and we want to take it all the way up to steam at 102 degrees Celsius. So sometimes when you're doing a problem like this, it's kind of helpful to maybe have a curve like this and just kind of visualize sort of where you're at. So let's take a look at this. This is going to happen in multiple steps along the way. It's not just going to be only one calculation step. So here's the deal. The first step is I'm starting at minus 3.5 degrees Celsius. Maybe I'll change my color here. I'm going to say I'm starting like down here. So the first thing that will happen is I got to take it from ice at minus 3.5 degrees to basically ice at 0 degrees. So this is going to be really my first kind of step that I'm going to do here, which is just that conversion, taking ice from the minus 3.5 degrees to the 0 degrees. Now, when I do that in my first step, I'm going to take ice at minus 3.5 degrees Celsius to ice at 0 degrees Celsius. And that is still solid all the way through, but my temperature is changing. So again, this is going to be a specific heat calculation. And we're going to use the specific heat equation here. We have our mass, which is 75 grams. Once again, we want to make sure that we do use the correct specific heat capacity. And remember, as I mentioned a second ago, for ice, it's about 2.09 joules per gram per degree Celsius. Remember that when we are changing it, talked about previously, we always want to go final minus initial. So in this case, this is going to be 0 degrees Celsius minus our initial, which was negative 3.5 degrees Celsius. And we're going to end up with here for our very first set, 75 times 2.09 times basically 3.5. And that's going to end up with 548.6 joules of energy. That amount of energy, essentially the energy to do just that little move there on the graph. Take it from ice at minus 3.5 degrees to ice at 0 degrees. By the way, that is increasing the temperature. It's an endothermic process, and that is why we ended up with a positive value here, right? So again, that final minus initial for temperature is important, because if you did it the other way, you would end up with a negative, which would be exothermic and not what's happening in this case, right? So if we come to our graph, we're now sitting basically right here. We're at ice at 0 degrees. And now what we need to do is take it from ice at 0 degrees to liquid water at 0 degrees. Not changing the temperature, changing the phase. And again, this happens at the normal melting point. So the second step is coming across here basically and doing that phase transition and taking it from solid to liquid. That, again, as I mentioned a second ago, is the heat of fusion that we want to use to do that. So the step number 2 is to take it from ice at 0 degrees Celsius to liquid water at 0 degrees Celsius. I'm going to use the heat of fusion that has joules in it, so everything's the same units. You could use the moles, kilojoules per mole, but you got to do some conversions. So the delta H of fusion, again for water, is a roughly 335 joules per gram. So we know that we have 75 grams of ice at this point. We will use our heat of fusion here, which will be positive since it's endothermic as well. The grams will cancel. 335. That's going to give us 25,125 joules. This energy here is again the energy to do nothing more than solid liquid. Again, changing the temperature like that. So again, we're getting close to where we want to get. Not really, but maybe we'll make a big move here. We're now sitting basically at this point at the very bottom at liquid water at 0 degrees. So the next thing that we really need to do is take it from liquid water at 0 degrees all the way up to the boiling point. So that's a big jump at least. So number 3 there, we're going to take it from liquid water at 0 degrees to basically liquid water at 100 degrees, which is the normal boiling point for water. So that is our transition. So all the way up that orange little bad line I just drew there, that is all liquid water. So that's the same phase, but we're changing the temperature. So again, this is going to take us back to our specific heat equation. So we're going to use our specific heat equation to do the third step here, which is we're taking liquid water at 0 degrees Celsius to liquid water at 100 degrees. And once again, so we're going to go with our Q is equal to ms delta T. Our M is still 75 grams. Now that we are in liquid water, we could use the normal heat capacity for liquid water, which is that 4.184 number we used previously. And again, we want to do final temperature, which is 100 degrees, minus initial temperature, which is 0 degrees. And that's going to get us here about 31,380 joules of energy transition from taking liquid water to liquid water at 100 degrees. All right, we're getting close. We're now sitting at the boiling point transition. So we're sitting at liquid water at 100 degrees. And the next thing that we have to do is take it from 100 degrees liquid water. We now want to transition to 100 degrees steam. And that's going to be our delta H of vaporization to do that. Again, we're going to change the phase here, but not the temperature, which again occurs as we do the phase transition. So we're going to use for our fourth step here, the heat of vaporization. Take it from liquid water at 100 degrees Celsius to steam, which is basically gas at 100 degrees Celsius. That is going to be our delta H of vaporization. I am going to use again the joule version of that number so that I have joule. And we're going to take our 75 grams of water at this point, use our heat of vaporization, 2260 joules per gram. Grams cancel with a lot. 169,000 joules. That transition. By the way, just as a note, if we look at how much energy was required to do the solid to liquid transition, about 25,000 joules. To do the transition from liquid to gas, about 170,000 joules, right? So a lot more energy required, again, to do that transition going from liquid to gas, as you got to get everybody away from everybody and broken apart, so a lot more energy. We are close, I think. We are now sitting at steam at 100 degrees. So the last thing we need to do is take it from steam at 100 degrees to steam at, what was it, 102 degrees. So this again is same phase, changing temperature back to specific heat capacity and specific heat equation here. So we're going to use our Q is equal to ms delta T. And step number 5, steam at 100 degrees Celsius to steam at 102 degrees. So Q is equal to ms delta T. Our M is still 75 grams. Once again, just like we did with ice, we want to make sure that we do use the correct specific heat capacity for steam, which is about 2.03 joules per gram per degree Celsius. Once again, not the 4.184 number, as it's not liquid water at this point. And we want to do final temperature 102 minus our initial 100. And we're going to end up with here 5 times 2.03 times basically there. And that's going to be about 304.5 joules here. First off, any questions on that there? Now we want to know the question, which is how much energy is required to do all of that? So each for individual energy steps, and as we talked about with energy, it is a state function. Doesn't matter how long it takes you to get there. You basically are just going to add up all the steps here. So if we want the total amount of energy, our total energy in this case would be our energy of step 1 plus our energy of step 2 plus our energy of step 3 plus our energy of step 4 plus our energy of step 5, which if we add those guys together, 304.5, 169,500 plus 31,380 plus 25,125 and 548.6. That's going to give us a total amount of energy to do this of 226,858 0.1 joules. We'll round it here to about 227 kilojoules divided by 1,000 in this case. And you'll end up with about 227 kilojoules. That is a endothermic right all the way through. Everybody's positive, which is what's happening as we go from solid to liquid to gas. Energy has to be put in. All endothermic processes. Stuff in here. What would be the only difference if I started with steam and ended with ice? What would be the only difference here? It'd be negative, yeah. So all the steps should end up being negative. The numbers will be exactly the same. You would end up with negative 227 kilojoules. As if we were going the other direction, these guys would reverse, and that would give you a negative number. This would be negative if you were going the other direction. This would be reverse, which would be negative. That would give you negative. These would be reversed and give you negative. So again, it would take the same amount of energy, no matter which way negative or positive, indicating and with the R X kind of chapter 10 that we did earlier, with the